But thankfully I had my freshman this year to fix it. Thankfully, I don't know how much was screwed up. I did have to redo some of it from last year only because the zip ties weren't pulled tightly enough. So there was too much wobble in it. But otherwise it was put together correctly. Okay. Now, here is the problem. And the problem that we'll struggle with through this chapter. What's the proper time, and as we get into other things, what's the proper length and momentum and whatever, and what is the dilated or at least affected version? So we were talking about this at the very end yesterday. Imagine a so-called stationary observer on Earth and a so-called moving observer on a ship. Both emit a flash of light every 5 minutes by their reckoning. The relative speed is high, 0.8 c, let's say. How long between the other's flashes would each observer time? So Schuyler actually came up with this just as you ladies left yesterday. He actually came up with this really quite good way to look at it and be able to see that although it's maybe a longer time, it is going to be consistent each time. So what he had was a graph. And pretty straightforward, a distance versus a time.
Very big time.
And he had the ship here. We'll start at 0 and then just start moving away. And so that's our ship speed at 0.8 c. And then every 5 minutes, every 5 minutes there's a flash of light emitted at 0 distance at Earth. Okay, so that would be, let's say, here, 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 and so forth. But that's traveling faster, obviously, than the 0.8 c. So it would be a steeper slope. So we might have something like this. And it'd be the same steep slope for all of them. Okay.
Oh my gosh. I like it.
So it's definitely a delayed time, is maybe even longer, but it is a consistent time. Now here's the problem though, because the ship is also emitting some light. So if the ship emits it here, it's still going that way, but it's decreasing in time. This one will be a lot harder. So it would be the same slope, the reciprocal slope, so same steepness, but now negative, and that's going to be really tough.
So it's a triangle.
Maybe, it could be.
Negative
Who knows? I screwed up this one. It would be back. And so the person on Earth would also measure a longer time than 5 minutes, but it would be a consistent time between flashes, same as on the ship. This proves a problem, though, because now you're observing something on the other thing moving, and whoever the observer is always going to measure the other clock, so the clock that is not with him, as measuring a different amount of time. So, which one do you use to find the proper time? This is something that Jacob was actually working on this morning that he found helpful to him, so I want to pass that along to you.
Yay.
You can, the way I think of it is, think if the event that you're trying to find is, say, how much does a person on the ship age compared to a person outside? The person on the ship has the clock that counts, the proper timing for that. The way that he was thinking of it was, picture that little knot that we've been using as a clock. So he drew a little face on the clock, little hands. Okay, and then the delta t, he put a little line down here because that's on solid ground. That's because the Earth isn't moving relative to most of the rest of the universe like a spaceship would. And that's what he was using to help him remember which one is which. This delta t is basically, or delta t naught is basically always going to be on the ship. the delta t will be at the still observer, and still only means relative to most of the stuff around him or her. Whereas this delta t naught would be the one moving through that space. So most of us would agree. Now, certainly there are more complicated situations where they're both moving away from the planet that we could consider, but we tend not to. Right? This is an introductory course to it, or section on it. Okay. So, and we will continue, of course, to practice this. What I'd like you to do over the weekend is work on the first homework set, particularly on the sections, or the questions on time dilation, but we will get to the next section as well. Monday I've got scheduled as a work day, so we'll do a couple of examples, whatever we don't get to on this next topic today, we will do Monday. But then we'll have work time too, so hopefully a fair bit of it. And if you can come in and say, look, I tried these, this one worked okay, solutions are up online again, but I don't get this one at all, that is a really good, or I don't get this part of this one, that is a good place to start. Yeah?
On the one we did before, like Back to the Future.
Yep.
For delta t0, you did a different equation than we did the first time.
No, I might have rearranged the equation. Right? So our equation was that delta t is equal to delta t naught over r1 minus v squared over c squared. Now if I rearrange that to find delta t naught, which is what did we? No, we used that one.
We did delta t naught equals delta t times square root of 1 minus...
That's true, although I don't think we did it for this one.
Back to the Future.
But yeah, that's... Oh, okay, the one before this. Yeah, that's just rearranging this. I just multiplied by that thing on the bottom. Sometimes, just the regular math, sometimes we'll abbreviate that as gamma, which is another Greek letter. And then it might be a little easier to see. If I want to get delta t naught, all I have to do is multiply both sides by gamma. And that, of course, is the square root of 1 minus v squared over c squared. Gamma is used a lot, and I forget if it's this or if it's the fraction of 1 over this, but it's used a lot with this because we're going to keep seeing that that radical crop up on almost all of our calculations. So let's take a look at some of them. Let's take a look at another result from this. We call it length contraction. Yeah, that was like hearing. So here, there are certain things we can say when two things are moving relative to another. One is that the relative velocity between the two observers is measured the same by both. There's no proper person. There's nothing that we can say is still in the universe. So, that being said, we can't say one thing is actually moving and the other is not, only that they are moving relative to one another. And because of that, both of those observers are going to measure their relative speed between them the same. Second thing we can say is that the elapsed time between events is different depending on who's observing it. So that's the clapper on the ship will be appearing to himself to clap once per second, but someone off the ship would look like a slower time. It would once every 2.5 seconds, say. This implies different distance, and we touched on that. That really bothered Kayla yesterday, because how could something go 8.64 light years in less time than you would measure light to take? Right? So an Earth observer has no problem. It would take our spaceship a little over 17 years to get there, but that person on the spaceship we said was just a few years. I forget how much. 3.5. Okay. So far less time. So how could that be? Light would take 8.64 years to get there. So nobody else could go the same distance in less time, and that is absolutely true. Therefore, they must not be going the same distance. So let's look at that. I think I actually want to put in my, yes, I want to do my derivation right now. So let's explore this. This one's actually really a short one. It's sadly short compared to the others. Okay, so we've got Earth here. It's the so-called still part. And we've got our rocket ship.
Sounds like a phone.
Not my phone.
It is a phone.
Alright. Rocket ship speeding away at some velocity v. Now, that v is measured the same whether you're measuring it from Earth to the ship or the ship to Earth. Both observers would agree to that. Now, if we're going out to some distant star, say Sirius here, Earth is definitely going, we've made good measurements of that distance. So we know the distance between Earth and the star Sirius. We're not really moving relative to each other, so we can say that that's pretty concrete. So an Earth observer would say that that velocity is equal to some length, and this is an actual length by an observer not moving relative to it. So we're going to use our not again. The person on Earth measuring the distance between Earth and the star is not moving relative to Earth and the star. And that always means that you get the proper measurement. However, the person measuring how long it takes, the clock is traveling with the ship. So we can't measure the proper time, we measure the dilated time. This is the same as what we were seeing with hypothetical Tom. He was measuring on his ship delta T naught. The Earth girlfriend left behind to wait, probably wouldn't, was measuring delta T, the dilated time, the larger time. The ship observer now is still going to measure velocity. That's going to be the same regardless. And as we said, the proper time. However, we have to leave in for this the fact that, and maybe we can prove that it is the same, but that it could be some other distance. Now you're moving with respect to that measurement, so you don't always get to choose that yours is the correct measurement, the proper measurement. But what we can say is these two velocities are the same as each other. So combining these two, we can say that this, the L naught over delta T, must be equal to the L, the length or the distance the ship would measure, divided by the time the ship would measure. Delta T, we already have an expression for it. And so I'm going to put in our first big equation in for that. So that would be delta T naught divided by that radical of 1 minus v squared over c squared. And that would still be equal then to the other side, L over T naught, delta T naught.
Would you put velocity as v1 and v2, or would you just keep...
Remember, they measure the same velocity. So no, we don't, because that's one of the things. We can't say one person is moving and the other is not. They're both moving relative to each other, and that's all we can say. Yes, ma'am?
Why did you put different stuff on the bottom?
Because I know where I'm going.
Well, what is it?
It's delta T. Remember our first equation was delta T naught divided by the radical. So that's why I put it in there. But now, look what we can do. We've got a delta T on the bottom of both of these.
Why do we have a delta T naught and a delta T naught?
I substituted,
Oh, okay.
right, delta T is equal to delta T naught over that radical. But now we have delta T naught on the bottom, so we cross that out, replace it with a 1. Delta T on the bottom, cross it out, replace it to 1. And we get our second big equation, just rewriting what's left here. L is on my right. On the bottom, I have L naught over 1 over the radical, which would bring that radical back up to the top. B squared over C squared. That is our next big one. And that says that these two observers are not going to measure the same distance between 2 points, depending on how fast they are moving relative to each other. Yep.
How did you cross out the delta T knots?
They're the same. They're both on the bottom. So x over 4 equals y over 4. I can cross out the 4's. Yes, Elsa.
So would one with the shorter time also measure the shorter length?
Well, let's find out. Let's find out. Let's see what this means. L naught would be the distance that you would measure if you are not moving relative to the beginning and ending points. So that might be our 8.64 light years, for example. What is this fraction going to look like? What v squared, how does v squared, the speed of any moving thing, compare to c squared?
V squared is always smaller.
It's always smaller. So this will be 1 minus a fraction that's somewhat less than 1. But it's going to be positive and less than 1. So when we take the square root, it'll still be less than 1. So our measurement made by the person on the ship will be the original measurement times something less than 1. So yes, it will always be shorter if you are moving relative to the beginning and ending points. That means your distance from here to Rochester, if you are precise enough, will be different measured from your car than it would, say, from an aerial photograph taken all at once. Because that aerial photograph is essentially still. I know, it's good. It's good stuff. Oh, yes?
Go over how you got that again with the...
No, but remember that I'm putting this up on the video, so you are free to, if you want to see the derivations again, go ahead and watch that. I've been pretty good. I've been getting them up by 8 or 9 in the evening, so they're available at any time thereafter. Mm-hmm.
So wait, what you just said is saying whenever you move, the distance between point A and B is shorter when you're moving?
Yep.
Okay.
Which is kind of nice, because that means your trips are that much shorter.
Not much, on our speed.
We should do a couple of these too, just to show if this, and we can kind of highlight that here. If you're traveling in your car, your velocity is probably on the order of 30 meters per second, 20 to 30. So that would be 30, v squared would be 30 meters per second squared, divided by the square of the speed of light, 3.00 times 10 to the 8. Squared. That is really close to 0, right there. So 1 minus it is really close to 1. The square root of that is also really close to 1. So essentially you're measuring the proper distance at that point, because your speed is so much less than the speed of light. We see the same thing for time dilation. This fraction becomes so small
So it's
that
less
it's
time
negligible.
dilation, but more distance dilation.
Same amount either way. Same factor. Yes, Chris.
So on the ship,
Oh, Krista.
Can you explain what L and L are?
Yes. And we might, let's double check, see if I don't have that. So yes, L naught, just like before, the naught means proper. So L naught means, so definite proper distance or proper length. Proper means the measurement made by someone who is not moving relative to that measurement. So the beginning and end points.
That would be like someone standing on Earth.
Right. Measuring the distance to that star.
I thought that was the one moving with it because it's kind of
L is the distance measured by the person who is. So we usually call that a contracted distance.
How not goes with changing time, and how it goes with changing time.
Right, they kind of flip-flop because of it. Because usually if we are measuring the time it takes for that an astronaut experiences, that would be a clock on board the ship. Right? So that's measuring the time that the astronaut experiences. The distance is better measured because the beginning and ending points aren't changing from the Earth. So they do sort of flip-flop with that. Mm-hmm.
So L is the length based on where we are at Earth?
L naught, we are on Earth are not moving relative to the star, correct? Or very little. So we can measure L naught, the proper length. That's the one that's that's measured by an observer not moving relative to it. We are not moving relative to the beginning and ending points, so we can make a good measurement for that. It is sort of the opposite of time. Mm-hmm. Yep.
I thought you said that time, the one with the circle, was the.
In time it is, yep. And so that trick with Jacob, he hasn't done a lot yet with like contraction. So I don't know if it will hold up. I offer it merely as another way to look at it. That might make a good connection with people. So let's look at our twins again.
That's your
This one is. Good afternoon.
Here's please go to the office, please.
Yep. No, if you wanted to turn it off, that would be fine. Yeah, it's done. There's a big switch on the left-hand side. Yep. Okay, thanks. Bye.
How do I turn off the bomb?
Yeah, the big switch. Okay, so we're gonna consider our twins' trip to and from Sirius. We had a relative speed of 0.980 c, so that's not going to change here. We'll keep the same information. Turn my pen on.
Ben stayed home.
I believe Ben stayed home. Yep. Chad is in a ship to Sirius, and Ben is on there. Okay. That was from our previous problem. How long did it take for the trip according to Ben? Flip back. I think it was...
17.6.
That sounds right.
It's either 0.6 or
0.6 years?
Yep, 0.6.
Okay. Now, let's figure out what Ben is on Earth. How far of a distance did he measure to Sirius? It was like 8.64. So double that, and we had the 17.3 light years, 'cause if we look at the round trip.
That's the 17.3.
Now, how long did Chad measure the trip to take?
3.5.
3.5 years. And of course, my next question will be, let's figure out the distance that Chad said that it was. Well, we can do that, I think, a couple of different ways, right? We could use his velocity and the time. That would work. And then we're going to check it with our equation over there to double check that that works.
So we want to hold on to that equation, right?
Yeah, oh yeah, that's another biggie. Along with the time dilation, that's huge. So let's do it both ways, just to, sanity check. So if we do velocity equals distance over time, just our typical one, using what Chad measures for each of these things, we could rearrange and find the distance that Chad does, which will be our L, not our L, would be equal to his velocity times the time that he measures, which would be, as we said, the delta T naught. So we said 0.98 c times 3.5 years. This will convert into units of light years when we measure it, because we've got the light part and the year part. So we don't have to put in the meters per second and then convert it in any way. 3.4, okay. Light years. Let's now go and check what we'd find with our new equation. Based on the proper length that Ben would measure, because he's not moving with regard to it, and find Chad's length here. So we'd have our total distance 17.3 light years.
So what's the light years for Ben? Right up for Chad?
This is Chad's measurement now. We're trying it two different ways. Here's first. 1 minus our 0.980 c, square that, divided by c squared. And of course that cancels out c's. But we do still have to square that 0.98. It's the same, don't we?
Kind of. This is 3.44, whereas before it was 3.43.
Well, but we had already rounded this a little bit. So since we had, that's good. You made me nervous there for a moment. So 3.44 light years. Yeah. Essentially the same with a little bit of rounding error. And the reason is, when we figured out this delta t, we already had that radical in, so we already changed that. Anyway, so in answer to Kayla's question yesterday, no, you can't travel faster than the speed of light. It just so happens that when you're traveling that fast, you're not going the same distance. See? Easy.
That answers a lot.
Yes.
So when you're going that fast, is the distance getting shorter or are you getting longer?
The distance is shorter. The measured distance, the distance that you measured while on your ship going at 0.98 c between Earth and Sirius, if you had an odometer on it, would be 3.44 light years, rather than the 17.3 light years that you'd measure from Earth. Yes, Scott?
What would happen if you put a value in for the speed greater than 1?
Can't go faster than the speed of light.
But we don't know that yet. We haven't gotten there. So let's see. So let's say that this was 1.1 c squared. So it would be a square of 1.1, which is I think 1.21. What's 1 minus 1.21? Negative 0.21. What's the square root of that?
Imaginary number.
It's an imaginary number. It doesn't work.
I squared.
But we're not squaring I.
Yeah, no.
Oh, I times the square root. Yeah. But that has no physical meaning. It's used a lot in quantum mechanics, imaginary numbers. I have never used it in special relativity. Doesn't mean that it, especially when you get into general, which is more complicated, that you can't. But I have never seen it. The explanation for imaginary numbers is, wait for it, pretty complex. It's harder to explain and understand even than this, what those imaginary numbers signify. But in this case it means, no, not physically possible.
Oh yeah, you can't take a point times a point and a point. Maybe the point would be bigger.
Smaller.
I'm just thinking to myself here.
Okay.
Not trying to
Maybe
make
smaller. You say 0.5 times 0.5 is 0.5.
Yeah. Yeah, okay, so that's where you were, yeah,
Yeah,
just to
trying
see
to
that.
say.
Okay, let's try another one. Big squeeze.
Oh, no, I'm good.
An outside observer sees a rocket speed by a stationary, at least according to that observer, asteroid. Both the asteroid and the rocket appear to be the same length. Okay, so the observer is still compared to that asteroid. If the rocket rest length, if the rest lengths are 25 meters for the asteroid and 35 meters for the rocket, how fast must the rocket be moving relative to the asteroid and therefore the observer?
So the rocket's been condensed.
Definitely, its normal speed or its normal length is, if you were measuring it while on it, would be 35 meters. If you were measuring it while it zipped past you, it would be 25 meters. It would not just look 25 meters. It would be 25 meters. Ding, ding, ding. No, he's gone for wrestling. Okay, so let's do this. And again, the hard part is deciding what's L, what's L not. So we're looking at the ship and trying to figure out how fast the ship is going. If you were moving along with the ship, you would measure L naught. According to the description here, what would you measure for L naught?
25.
Because that observer is moving along with the ship?
Isn't L not the asteroid?
Yes, L naught is the asteroid, exactly.
Huh?
I'm not asking about the asteroid here. I'm asking how fast must the rocket be moving? So if you were with the rocket, you would measure its rest's length, which is 35 meters. However, when it's moving past you, you measure it to be the same as that asteroid, which is 25 meters. That makes this the L.
So
Remember that knot, the knot value always is measured when you're moving with the thing you're measuring. Mm-hmm.
Didn't you say, oh, this?
Didn't I say what?
That was only for time.
No, it's
No.
the same for time. If you're
Because-
moving with your clock, you're measuring delta T naught.
In the previous problem we had on Earth not moving relative to the rock, to Sirius or whatever
Yep.
the place was, we had that with L naught, but now we don't.
Right. It can be different. Because if you're measuring a ship, how can you get the proper length? You can only get it if you're moving with the ship. If that ship slows down and parks next to you later, you're going to measure this proper length at 35 meters. But not if it's moving. There you can't measure the proper length. Only if you're moving with it. So we want to rearrange this and get the speed, the V. So first thing I need to do, divide by my L naught.
What shrinks as it speeds up?
What?
Does a rocket shrink as it speeds up?
Yeah. But not to a person on the rocket. A person on the rocket moving with it always measures the proper length.
So they're shrinking too.
Mm-hmm.
Or are we
Square this. Well, yeah, and so you would, yeah. Well, but if you're looking outside of the rocket, you also see everything else shrink because it's moving relative to you.
Don't you think it's much more realistic
I
that
don't know.
everything except the rocket is changing?
Everything's changing. That's the real answer.
So if that rocket goes by, we're going to have messed up in the head. Things are going to shrink. and
We're
grow.
going to subtract 1 from both sides. So we'd have L squared over L naught squared minus 1, and that's equal to negative v squared over c squared. I'm going to multiply by negative c squared, but I'm only going to distribute the negative 1. I'm going to keep the c squared out of there because I know I'm going to take the square root the next step. So I have c squared. That'd be a negative L squared over L naught plus 1. So just because we're used to doing it this way, I'm going to flip those two. And now I'm going to take the square root of both sides. So the velocity would be equal to c times my square root, 1 minus L squared over L naught squared. And now I've run out of room here, but we can put in the values that we've got up in front. I can put it over here, I guess. C times 1 minus my L is 25 meters squared over my L naught, 35 meters. I'll square that.
Probably can't see too much of that on here.
Possibly not.
Too bad.
Yes, Matt.
Why in the third one is it a negative?
No, they can see all that. In the third one, is it a negative one? Because
First row, third one down. It's a negative.
because I wrote that I was going to subtract it from both sides. Okay, what do we get?
You didn't times that by C though.
Well, it's 10.
0.70 what?
C.
What's between? We get one more.
Oh, it's 0.699.
0.699. Okay.
Yeah.
Jeez.
0.699.
C. Yep. Pretty fast, I guess.
So, should we, just in case, hold on to the v equals c square root 1 minus L squared over...
Wouldn't probably need that again, but we will want that speed, for sure. Because now my next question is, how big does the asteroid appear to be to an observer on the rocket, while the rocket, of course, is going past it?
You just want to fry our brains, don't you?
Let's find out. Are we okay? I know it's getting tough, but are we okay with how to figure out what L naught and L are? Well, let's try it again then. You're on the rocket ship. You're looking at this asteroid that is outside the rocket ship that you are moving relative to. Can you accurately measure its proper length while you are moving past it?
Not going the speed you are.
You cannot. So let's take a look at this rock at the. Take a look out of our window.
Does that mean
In fact, what would a person who is not moving relative to that asteroid measure its length to be?
30 or 25.
25. We already said that. So we are stationary and next to an asteroid that is also not moving relative to us. So we can measure that distance accurately. And we said it was 25.0 meters. In the ship, we can't. We could still measure it, but we can't call that the proper time because we're moving past it. So we don't know what L is. But we can find it. We can use that equation as is. We know that if we were still, based on the question, we would measure it at 25 meters in length. And we know our speed relative to it now is a 0.699 c.
Why can't we find the L?
Can I have your attention, please? Will the following sophomores please report to the office? Tyler Schmidt,
This is getting ridiculous.
Braden Halver,
Every
Dawson
day.
Grotjon, Brady
Every
Windows,
hour of every day.
Tyler Nagel, Jordan Newcomb, Dawson Burr, Nick Thiel, Austin Hoover, Bryce Fissler, Nick Fox, Wesley Hill, Colton Dottievit, Mitch Sawyer, Cadence Quent, Matthew Parrish, Maggie Mann, Carter Sven, Heather Koenig, Haley Hanna, Ben Schmidt, and Laura Eberly.
Read the list before you read it, or on your tongue. Please.
Okay, let's go back and finish this question up. Yes.
Why can't we find the original L of the ship?
We can. You know that we're on the ship. We could measure it.
Why is there a question mark then?
Because we're trying to find how big the asteroid appears to be. And L naught refers to if you were still next to it, you could measure its proper length. We are just asking, if we look out the window and use some sort of a measurement device, how long would it be as we were going past it? And this is how we find that. Which gives...
So pretty much once you can determine where L and not an L is, you're good. Like it's not too much work.
Well, none of it's... The math part isn't difficult. Yeah. The difficult part I've always found is determining, well, what's the proper measurement for whatever we're looking at.
Yeah.
That is definitely the difficult part.
You really gotta read it well, too.
You've got to read it very carefully, and you need the practice, which is fine. But that's what this practice is for. So I get 17.9 meters. So the ship, to a person stands out there floating in space, the ship appears to be, or is, 25 meters long as it goes past. The asteroid is 25 meters long as well. However, to a person on board the ship is 35 meters long and the asteroid is only 17.9 meters long.
Sweet.
Yes. I agree, hypothetical Tom.
So L naught is obviously 25 because you can't measure that 35 while you're standing inside the ship.
Right.
Kind of.
How would you measure it? That's my question.
So for Monday,
The picture had
yeah, you could have a picture, but you kind of have to know some distance to be able to use some trig to figure it out.
Some pixels to measure.
Yeah, well, that would only be an angular measurement in the picture. It's called. So you'd have to know the distance to it in order to measure that. Now that would not be changed. For Monday, give it a go on the homework. There is a reading selection that's marked on the first front page. Please read that in the text and then work on those. It's the stuff that we just talked about, but it's a different perspective. So that could be helpful.